Hello class, welcome to my video presentation. Today I will be talking to you about the complexity, entropy, causality plane and how we can use it to categorize various songs and sounds. Now, originally I started off by following this paper here that I did my literature review on, where they used the complexity, entropy, causality plane to measure the market efficiency of various cryptocurrencies such as Bitcoin. It gave me underwhelming results, and later I discovered that the exact same technique could be used to categorize songs, which gave me nicer results with more to talk about. The complexity entropy causality plane combines the measure of permutation entropy and statistical complexity, which is essentially a measure of how chaotic a given time series is, and in the context of a financial market this might be interesting as it can be used to measure how predictable a market is, which may be interesting for making investment decisions. In the context of music, both Biro and Owl in their paper use the exact same measure to distinguish songs into various genres. And you can see here in the results, in their plane, you have jazz, classic, and tango all around this part of the plane, and you have techno on this part of the plane. So yeah, my motivation for this assignment was to try to replicate that. The permutation entropy is simply another way of measuring the Shannon entropy. What is different here though is how we calculate the probability distribution that then goes into the calculation. We begin by first looking at only the first n number of points in the time series. So yeah, we have x1 over here, x2 over here, x3 over here, and so on until you have xn over here. Then we choose an embedding dimension, which in our case we're going to choose 3, and then you create a list of all possible permutations that you can make with 3 objects. So yeah, we have 0, 1, 2, then we have 0, 2, 1, and all other possible permutations that you can make. To then actually create a probability distribution of permutations, we first count the total number of observations that we have. So let's say we have 300. And then for each permutation, the first distribution, for example, would be 55 over 300. And that's the probability of the first permutation happening. Probability of the second permutation occurring is 40 by 300. And we do that for all points. And then that gives us a probability distribution that we can then put into Shannon's entropy calculation. To then calculate the permutation entropy over the whole time series, we choose a step size, let's say 4, and we do the same for the next set of endpoints in our time series. So 1, 2, 3, 4, then we do the same for all these next set of points. If we then do this for over all points in the time series, then we get the permutation entropy as a function of time, which we can plot. Now, why might we be interested in the permutation entropy? Well, here's some code, and it produces these results. We have a time series of a sine wave over here, and a time series of a random walk over here. And then we have the corresponding permutation entropies over here and over here. Notice that in the sine wave, we have a high probability of this permutation occurring and a high probability of this permutation occurring, which corresponds to values going up and values going down this way. We also have low probabilities for these permutations occurring, which for this one, which is 0 to 1, corresponds to a pattern with a shape like this, which is quite unlikely to happen in this time series. It only happens here, 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 so pretty rarely compared to just continuously going up or down. Meanwhile, for a random walk, we have a much higher chance of these middle permutations occurring, which means we get a much flatter probability distribution compared to what we do up here, where it's pretty much flat like that, which is reflected in the entropy calculation. So you can see that the entropy for a random walk is much higher than that for the sine wave, which is much more structured, which means there is a higher level of surprise in a random walk compared to that of a sine wave. The other measure used in a complexity entropy causality plane is the statistical complexity shown here. It is essentially a measure of how much a calculated permutation entropy differs from that obtained by a perfectly flat probability distribution. It is simply the product of the normalized permutation entropy and a measure that's the so-called disequilibrium. We have P, which is just the calculated probability distribution from before, and then we have PE, which is nothing but just a perfectly flat probability distribution. So the disequilibrium is essentially a measure that compares how our measured permutation entropy differs from that of an equilibrium state. Now that we have discussed both measures, we can start looking at the complexity entropy causality plane and how different songs from different genres look like when we plot them onto the plane. Our first song is... that you got to listen to this beautiful song, this is what it looks like on the complexity entropy causality plane. We have my own results on the left, where I have definitely obtained the songs through 100% legal means, and I swear I didn't just download them from YouTube illegally. And we have the results produced by Ribeiro and Al on the right, whose results I'm trying to replicate. Unfortunately, our song genres are located on other parts of the plane compared to theirs, but nonetheless, different songs still appear on different parts of the plot. Our results make more sense when you compare them to the amplitude time series plots over here. In Furlise, for example, we have a long period with no sound in the sound file, which tends to give these trails over here. If we zoom into the time series plots, we can see that the songs which have low entropies tend to have a time series where the low frequency waves are clearly visible but no trouble apparent. So for example, this song here, which corresponds to this plot here, has low entropies and it sounds like this. Sometimes I feel like I wanna go back. This song has a clean but heavy bass and not much treble except for some sound effects here and there. Meanwhile, the song's Never Gonna Give You Up and the song First of the Year by Skrillex tend to have much higher frequencies visible in the time series compared to Wanna Go Bang, and therefore the entropy is much higher, which is visible in the plots. In conclusion, I have managed to build a complexity entropy causality plane that can distinguish songs, although not quite based on the genres as outlined in Ribeiro's paper. To continue on this project, I thought it would be a good idea to use the digital audio workstation named FL Studio to produce sounds and waveforms with the purpose of identifying how various types of sound look when they are plotted on the complexity entropy causality plane. Another possible direction that I could take this project is to create a complexity entropy causality plane that takes two-dimensional data as input and use it to analyze films. Although I believe this has not yet been done in the literature, so I don't quite know what the results of that would give, but it'd be worth experimenting around with and see if we can find any useful results.